Hello everybody, this is Marsha Tasnim and today I'm gonna give the presentation based on the paper which is SEApp bringing mandatory access control to Android app. I'm gonna start with the background of the study. The mitigation of security threats that characterize mobile operating system is the need to balance on one side to the high sensitivity of the information and on the other hand the need of user to install into the system a larger number of applications, often produced by unknown developer which may hide malicious functions. Uh, Preliminary screening is not enough for mitigation the security threats. Boundary should be specified by the user for a particular app operation. AC Linux implements the mandatory access control mechanism in OS, but stronger protection do not extend to regular apps such as untrusted app domain. Here, AC app give developer the ability to apply MAC to the internal structure of the app would provide more robust protection against other apps and internal vulnerabilities. There is currently no option to let the app developer control the use of MAC label as every component has complete access to the internal storage. Third-party libraries may abuse app privileges. Large and modular app developers find it difficult to fully control which components of an app are using sensitive data. The availability of a solution such as SEApp can greatly reduce such risk. It offers an easier way to do this compared to isolated process, as it permits to assign a domain to the process in which the component is executed and then configure the required permission at MAC label. A better compartmentalization can reduce the impact of internal vulnerabilities in modular app, since each module can be associated with a dedicated policy fragment. From a security and software engineering standpoint, AC app permits to separate the activities of security policy maintenance and development of new feature. Methodology. The idea is to separate the component into the different app process, regulate with the AC Linux the permission at process level. A component fall into a process based on its Android process value in the manifest. Policy module is processed at app installation time by a component of the system called AC app policy parser, which is responsible to verify that the policy is correct and doesn't introduce vulnerabilities into the system. Each app provides a policy module. The policy module lists the security context associated with process and files, like AC app context, file context, etc. When writing a policy, there is frequently the need to assign the same set of authorizations to multiple types to avoid the repetition of multiple allows declarations. It is convenient to refer to multiple types using a single entity, the type attributes. Each type attributes essentially represents the set of types that is produced by the expansion of its definition. The semantic is that each of the type that directly or indirectly appears as the source of an allow rule which is authorized to open with the specified permission on each of the type directly or indirectly appearing as the target. To preserve the overall consistency of AC Linux policy, the first requirement is that an app policy must not change the system policy and can only have an impact on process and resource associated with the app itself. The policy constraints are enforced at installation time, and runtime. In the block statement, the researcher detected the origin of types and attributes, like local defined within the policy module and the global defined by the system. Origin determines valid allows and type attribute set policy statement. For example, the use of type or attributes defined by other module which is prohibited. Trigger to allow statement, a dedicated analysis is performed by the SEApp policy parser. For each rule, the global origin of source and target types is determined. The researcher referred to the system origin as when the type is directly or indirectly associated with the system type in the expansion of its definition, while to local origin and otherwise. Based on the origin of source and target of each rule, there were 4 cases. Allow SS represents a direct modification of the system policy. Allow AA defines privilege internal to an app module. Allow AS when a local type needs to be granted a permission on the system type. Allow SA regulates how system component access internal type. But researchers need to ensure the interoperability with service crucial to the app lifecycle, so they introduce Marcos. Benefits is the safe by design. A predefined set of statements is added to the policy. No need for the app developer to know or understand system policy internals. The policy is not bypassable since the modules are loaded before any application starts. Developer willing to define its own policy module is expected to load it in the app package. At app installation, the package manager service inspects the APK to identify whether or not the current installation involves a policy module by looking for the policy directory at the root of the archive when app has a policy module attached to it. The package manager service extracts it and uses the researcher's policy module validates to verify the respect of all the constraints of AC policy and on the configuration files. In the case of violation of constraint, the app installation stops. Otherwise, the policy module is stored within data AC Linux in a dedicated directory identified by the package name. Then the package manager service invokes install through the installer to trigger the policy compliance with an access call to the select program. SEApp read the system AC policy fragments. The AC app Marcos and the AC policy fragments of the app policy module in the data AC Linux directory and build the binary policy. When the SEApp execution return and no compilation error have been raised, the binary policy is then read by, installed and loaded by AC Linux Android load policy, which is write the AC Linux load file. To load the policy file after init, the implementation of AC Linux in Android has been slightly modified. In particular, the developer modified the policy loading function within the AC Linux and changed the system policy to allow install to load the app policy module. Figure 5, as we can see, Android application design is based on the component. Each of them lives inside a process, can be seen as an entry point through which the system or the user can enter the app. To activate a component and assign Cronus message called intent containing both the reference to the target component and parameters needed for its execution has to be created. The intent is then routed by the system to the activity manager service via binder IPC. Before delivering the intent request to the target component, the activity manager service checks if the process in which the target component should be executed is already running. If not, the native service called Zygote is executed. Its role is to spawn and correctly set up the new application process. To achieve this, it first replicates itself by performing a fork, then using the input provided by the activity manager. Developer adopted the final configuration step, forcing Zygote to set the security context based on the SEApp context located data SE Linux package name. Process name is used to assign the proper context to the process when it starts before the logic of the process kicks in. In case the developer did not specify a domain, then Zygote uses the system SEApp context as fallback. After the correct labeling, the Activity Manager service finishes the configuration by binding the application class, launching the component, and finally delivering the intent message. Android application aiming to create a file can use the Java file abstraction. Each file creation request that is generated is captured by the Android runtime and then converted into the appropriate syscall. The result is the creation of target file to which a security context inherited from the parent directory is assigned. The separation between the file of the different app is enforced at Mac level. Context based on UID and SE Linux category is assigned. However, all the files stored in the same app folder are labeled with the app data file type. This is the introduction of project table. The policy files are split among multiple partitions, one of each device maintainer. For example, platform, SoC vendor, ODM, and OEM. This feature facilitates update to new version of Android, separating the Android OS frameworks from the device-specific low-level software written by the chip manufacturers. Yet each time a partition policy changes and on a device, compilation is required. The init process divides its operation in three stages. First stage is early mount, AC Linux setups. Second stage, the first stage mount the essential partitions alongside some other partitions specified as early mounted. Android 10 using an fstab file in the first stage RAM disk. In Android 9, lower adding fstab entries partition are mounted. Init enters the AC Linux setups. As the name suggests, this is the stage where init loads the AC Linux policy, as the data partition where the policy modules are stored is not yet mounted. It is not yet possible to integrate them with the policy of the system. Then, as last operation of the AC Linux setup stage, init re-execute itself to transition from the initial kernel domain to the init domain, entering the second stage. As the second stage start, init parses the init RC files and performs the built-in functions listed there, among them mounting the data partition. Now the policy modules are available, so the developer can produce the SEApp and the binary policy consisting of the integration among the system policy. the SEApp macros and the app policy modules. To trigger the build and reload of the policy, developer implemented a new built-in function and modify init.rc to call the function right after data is mounted. The policy is considered immediately after the data partition is available, and this ensured that the policy modules are loaded far before an application starts, making the policy not bypassable. Each time a new application is installed, all the policy fragments stored in the device have to be recompiled to produce the new binary policy. The installation time overhead then growth from the increase in the number of installed policy modules. To further analyze this aspect, developer repeated the installation of the top 100 free apps, adding to all the packages in 3 separate experiments the same basic, ordinary and huge policy configuration. The experimental result illustrated in figure 9. It shows that the use of huge policy modules introduce a non-negligible overhead. However, the policy configuration stimulates an edge case, as we do not expect to find 100 of them in a real scenario. To give a comparison, the huge policy declares 100 types. The file used to define all the file types of the system, declares the 314 types in Android 10. In table 5, we can see that it demonstrates that the performance of a stock version of the OS and AC app are equivalent, and also we observe that the AP apps willing to benefit of intra-app isolation features get from the use of AC app the same performance they would get from the use of remote component. And it also proves to outperform the isolated service, as the isolated process option forces the creation of a new process every time an isolated service that was previously unbinded, which is activated. This introduces a slowdown compared to the ACF service warm start, which instead benefits from the system caching mechanism. Finally, we can say that developer can use AC Linux to define domains that are internal to their apps in such a way that is possible to leverage the module that are already providing protection to the system. By mapping AC Linux domain to activities and services, developers can limit the impact that a vulnerability has on the app process and files. Researchers also describe in this paper that the change they introduced into the Androids and experimental evaluations shows that the overhead introduced by their proposal is compatible with the additional security guarantees. That's all about my presentation. I hope you guys enjoyed, and here's the reference that I have given which I have used for my presentation. Thank you.